Hey, we are going to do a series of lessons on variation. We're going to look at direct variation and inverse variation. We're starting with direct variation, and today we're only going to look at direct variation where the relationship is linear. So when it's graphed, it's a straight line. So what is direct variation? Here we go. Imagine I have a very big bucket and it's extremely straight. And I'm going to pour in water. Look, there's little markings on the side that shows the height or the depth of the water in the bucket. So when it's up to here, it's 5 centimeters high. This is 10 centimeters high. This is 15 centimeters high. I'll just write the unit there. And say I pour in 1 liter of water. The water level rises with 5 centimeters. So that's my first liter that I poured in. If I pour in another liter, of course, this makes a lot of sense. The water rises another 5 centimeters so that it reaches 10 centimeters. And you can imagine for each liter that I pour in, the water level rises with 5 centimeters. So for every 1 liter, right, it rises 5 centimeters. So the liters and the water level are in a relationship that we call direct variation. If we double the number of liters, say we go from 3 to 6 liters, we double the liters, that will double the water level, the depth of the water, right? It'll go from 15 to 30. That makes a lot of sense. So if we double the one variable, the other variable doubles as well. Let's try to roughly graph this relationship. Say our x-axis shows the liters that we pour in, and the y-axis shows us the depth of the water. So for a direct variation, one thing that is true is when x equals 0, then y also equals 0. So for direct variation, your line is going to go through the origin. It's going to touch at 0, 0. So when x is 0, so you haven't poured in any water, then your water level is also going to be 0, right? And this is true for all direct variation. Let's quickly 10, 20, 30, and say these are our liters. 5 and 6 is here, and I can't write it anymore, that's okay. When 1 liter is in, there's 5 centimeters. For 2 liters, there's 10 centimeters. See? 4, 20, and the line would look something like this. It's a linear relationship. When you graph it, it's a straight line, right? And it passes through the origin. Straight line. And one thing we also noticed is that when we double the number of liters, the depth also doubles. When we triple the number of liters, the depth also triples. We have a nice symbol for proportionality. Like that, which is what does that look like? It looks like the infinity sign symbol with like this part cut off. Y is directly proportional to X, right? This symbol means is directly proportional to. And for linear direct variation, the relationship will be expressed with the formula y equals k times x. Ooh, I should do my squirrely x. Because you know that any straight line that passes through the origin can be described by a formula in this shape, right? It reminds us a lot of y equals mx plus c, where c, the y-intercept, is 0. See, the y-intercept is always 0. So the equation of two variables that are in directly proportional, c is always 0, so we can leave this out, and it's just in this shape. Y equals the slope times x, right? Right, and k in this case, so we don't use the letter m, which we usually use in a straight line equation, but we have a k now, and k is called the constant because it's one number, right? Constant of proportionality. So really, it's the slope of the line when we graph the relationship. But in this setting of a direct variation, we call it the constant of proportionality. We use different terms to describe direct variation. I probably have been using them all mixed up already, and you may be confused now. We can say y is directly proportional to x. We can also say y is proportional to x. When we say that, we really mean the same thing. We can say y varies directly to x or with x, or we can say y varies with x or to x. So sometimes we leave out the word directly. See that? And we can say it's proportional, or we can say it varies with the other variable. Okay, this is kind of theoretical. Let's look at an example. What if someone told you y is directly proportional to x, and why don't we just write this? That's what that means. And y equals 48 when x equals 8. Okay, so the two are directly proportional, and another thing we know is that when x is 8, y equals 48. Now, can we find the equation, the formula for y in terms of x? So can we find the formula like this to find y in terms of x? So really all we need to find is the k, right? Is the constant of proportionality. So what do? We just plug in the values that we know. We know that when y is 48, x was 8, k8. And now we just solve for k to find this constant. We divide both sides by 8. 48 divided by 8 is 6. 6 equals k. So the formula for y in terms of x is this, but we found our k. K is 6, so we write it like that. And now we can, now with this formula, we have fully described the relationship between y and x. We can find any y value, any x value when we've been given the other value, right? So if I give you any value for x, you'll be able to find y. If I give you any value for y, you'll be able to find x, right? So this fully describes the relationship that these two guys are in. All right. We could also now find the value of y when x is 2.5. So what I just told you that you're able to do, let's do one of those. What does y equal when x equals 2.5? Well, we plug in 2.5 for x. Y equals 6 times 2.5. That means y equals, what is 6 times 2.5? It's 3 times 5 is 15. Right? So when x is 2.5, y equals 15. Easy enough. I think you're ready to do some on your own. Good luck.